Since their first appearance on the planet millions of years ago, plants have been an intrinsic element in the development of the Earth system. They have reworked the planet to suit their own needs, altering the chemistry of our oceans, the composition of our atmosphere, and the nature of our physical landscape. During the Ordovician, 470 million years ago, plants emerged into a world radically different to the one we recognize today. While life teemed in the Earth's oceans, the land had yet to be seeded by life. The first plants to colonize the land thrived in damp environments. These organisms lacked systems to transport water around their bodies, and today are known as bryophytes. Their numbers include moss, liver, and hornworts. The evolution of vascular tissue and roots during the Silurian and Devonian meant that tracheophytes, or vascular plants as they're more commonly known, could tolerate drier conditions than previously. This facilitated a huge biodiversification of plant life, opening new niches and an explosion of forms, with great consequences to the Earth system. The development of roots facilitated the physical and chemical breakdown of the underlying rocks. Minerals and nutrients were then released into the soils, which leached into the world's rivers and resulted in the eutrophication and subsequent anoxia of extensive areas of the world's oceans. This contributed in part to a series of mass extinction events collectively known as the End Devonian mass extinction, causing an estimated loss of nearly half of all marine genera. The development of the root and vascular system in plants is closely tied to a great shift in river systems in the geological record. Prior to this, river banks were unconsolidated and easily eroded, forming braided networks of channels. Roots acted to bind the sediment and soil particles that made up these banks, increasing their structural integrity and promoting the formation of meandering rivers. This simple change opened multiple new ecological niches for plants to thrive in, and allowed for a major shift in atmospheric composition, moving into the Carboniferous. The warm and swampy environments of the Carboniferous hosted a plethora of diverse flora. To survive in this waterlogged world, plants elevated themselves above the marshy surface, occupying a niche now held by trees and their relatives. The great success of this evolutionary strategy is now seen in the vast coal beds associated with these Carboniferous environments.
So these were tree-like, but not trees in the way that we think of them today. So they grew in the Carboniferous in particular and into the Permian a little bit as well. And they grew up to 30 meters or so in height. They could have trunks that were over 1 meter wide. But unlike trees today, they first of all were not seed-bearing, so they reproduced by spores, so a little bit closer in some ways to things like quillworts or even moss than to trees that we have today. And these, of course, were an incredibly important component of what we now know as kind of the coal forests almost. So lots of the coal that humanity has burned since the 1800s has come from the ecosystem that was originally, at least in part, dominated by these lepidodendron trees.
Trees work out how to make an entire axis out of it, how to make a trunk, how to make woody roots, how to make branches. And so that enhances their carbon capture, it makes them much bigger, and it also begins a whole process of real soil formation as they get much deeper and begin breaking up and weathering rock.
The development of lignin had significant impacts on the Earth's atmosphere. By drawing down carbon dioxide during coal formation and releasing oxygen during respiration, the fundamental ratios of these atmospheric gases was shifted. Oxygen concentrations were a little under double what they are today. A consequence of these elevated oxygen levels were huge arthropods such as Arthroplura and Meganuria, which thrived in the damp, swampy environments of the Carboniferous, as their growth was previously limited by oxygen availability. This surge in plant productivity resulted in a reduction in atmospheric concentrations of carbon dioxide, and a global cooling period brought about the lessening of the greenhouse effect. This resulted in the longest and most intense glaciation of the Phanerozoic. A series of environmental changes and extinction events opened up a variety of ecological niches. This facilitated the evolution and development of flowering plants during the Triassic, also known as angiosperms. They diversified rapidly during the Cretaceous and successfully became the most species-rich group of land plants to ever exist, currently making up 80% of the total land plant population. One of the most widespread and versatile of these flowering plants to develop were the grasses, also known as the Poaceae. They're adapted to outcompete trees and shrubs in areas where water availability is limited. They adapted to thrive in the increasingly warm and arid conditions of the Cretaceous. Today, grasses can be found ranging from the Arctic tundra to the temperate prairies, occupying 40% of Earth's land cover. As we have seen throughout time, plants have had a profound impact on the natural structure of our planet over their 470 million year history. However, it could be argued that humanity has had the deeper and more profound impact on the planet's ecosystem over our relatively short existence. This manifests as agricultural monocultures, vast areas of deforestation, and the ever-growing sprawl of our urban centres that can be even seen from space.
I mean, human beings are a mass extinction event, we just are. And generally speaking, after a mass extinction event, you have a survival phase, you have a recovery phase, and then potentially you can get new biodiversity emerging. We are probably creating new ecological niches, maybe adapted to a hotter, drier world with fewer forests and fewer large animals, and that will drive new phases of plant survival and plant evolution. We have inherited a wonderful biodiversity from all of these past ages, and we should try and conserve what we can of it as best we can for human use, if not just for its own intrinsic value.